Hello there.
Tired eyes, never chasing for new highs anymore. I don't think I can pave the way with only dreams of yesterday. I realize we're nothing more than just a memory.
Good evening and welcome everybody, it's Obi-Wan Pez for Simplex Pachinko. We are doing some mathy type stuff tonight. Tonight we are currently on alternating series and then looking at power series. So we were looking at the tests the series test to determine whether or not a series will converge. And completed all those. Evening, Zach. You hate hard decisions? Right. I was trying to remember what this was. This was the looking at a set of the proper factors of a particular number, S of n, and then looking at sigma of n, which is all of the factors of any particular number, which includes the number itself. So we were trying to prove here with amicable numbers that we did in fact have this particular property, which looked really weird at first, but was like kind of obvious once we broke it down. But hey, that's math for you. Okay. Theorem is greater than test. Yeah, well. Also, you never have to apologize for not rating my channel. Alright, so here, with an alternating series, in your opinion, and one of your committee members who argued with you about during Master's Project proposal for a series unit, yeah. What, oh, did you just call them, like, the same name, but change test to theorem? Nice. Alright, so we got an alternating series, which is just having a term of -1 raised to the next,
Raiding party!
We got raided. Woo! Hey, Matt Fund, how are you? Good evening and welcome, everybody. If you don't know me already, my name's Obi-Wan Pez. This is N Simplex Pachenko. We do mathy stuff on Mondays and Wednesdays. Tonight being our usually like calculation kind of night. We're currently working on cracking the GRE math subject test, second edition from Princeton Review 2002. More or less, doesn't change all that much, but you know. Chat flexing in progress. Oh, thanks, Rex. Yeah, actually, Matt, I was on Zach's channel on the Obi-Wan. Yeah, this one over here. Where's my mouse? Mouse disappeared. It's terrible. Do 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 do. That one. So yeah, I was also on Zach's channel, and so thank you for sending myself over. Hope you all are having a good evening. What'd you get up to? And then also, woo! Touche, Rex, touche. Whatever shall I do with those 182,000 points that Obi-Wan has? You know what? We got to get Matt on this list too. So, if anybody is new here or hasn't been initiated into the EduTwitch math community over here, we have our list of other math helpers and really awesome people. So if you have not followed Math Pond, aka Matt, go ahead and do that. And then we have our other list here. We have Slim from the Academy of Useless Ideas, Dr. Gold from Actual Education, Don Factorial, Ian Stuckey, Zach from E to the 2I Pi, Meriwether Remark, Penn Center, Phobos Dream, Physics and Depression, Talos Teaches, and the Tutor Wizard. And we also have our friends from study groups who are often in our larger community as well. And these are people who are learning something and want you to learn it too. So go check them out. We have Rendeo, Math Spellbook, FizzBuzz, Suna Owl, and Walking Stick Library. If anybody knows a different pronunciation, feel free to yell at me. So currently we're looking at the alternating series theorem. Thank you, Zach. So to say that we have an alternating series, what does that actually mean? Given a sub k some sequence, -1 raised to the k plus 1 a sub k is going to be the corresponding alternating sequence. So it's the exact same sequence, but every other number is negative of the original. This then yields the sum, as k goes from 1 to infinity, of -1 raised to the k plus 1 times a sub k as the alternating series of, I suppose I should put of as well. As k goes from 1 to infinity. As long as a sub n is particularly non-negative, then we have some interesting properties that end up having going on over here. Music's hidden. Oh, I should probably mark that as well, because I did not. Thank you for reminding me. You probably didn't mean that, but you know. But I did not post this yet, so. This is my particular playlist that I use here. It is all from No Copyright Sounds. I have been getting some taps from both YouTube and Twitch on like, hey, you're playing copyrighted music. It's not doing anything other than just muting the music, or muting the entire stretch of video. But right, this is literally No Copyright Sounds. So, like, in theory, I don't think they have a leg to stand on. And interestingly enough, I did look up a particular company that had thrown a claim. I think it was AEI or something like that. And found that No Copyright Sounds has an injunction against them. So they have a court order that's been posted that's like, hey, you can't do this. So the next time that pops up on YouTube, I'll probably forward them the link to the court case. let them deal with it on that end. Okay. So the individual terms of a sub k are all going to be non-negative, so either positive or zero. Or we could end up making it the absolute value of a sub k is greater than or equal to 0, which is just literally by definition. The convergence test, or the convergence theorem, which comes out from this, right, this is the alternating series convergence theorem, as opposed to all the rest of the convergence theorems that we talked about last week. So if anybody does have any questions on, like, series theora, or series tests, you might know them as, feel free and watch that other one from last week, and we'll answer any other questions you might have. If you have any other questions about mathematics, you can ask me, or how to teach math, or how to approach a particular thing. I have some different, possibly interesting ideas, depending on your definition of interesting. And at the very least, a different perspective that I've done stuff for. Yeah. Thanks, Mavort. Yeah. I've also been slowly migrating in that particular direction. So I've been, like, unchecking the track numbers for whatever. And then saying, like, the thing that goes to Twitch is only going to be track 6, for instance. And currently, the issue is that all of my desktop audio is going through just literally desktop audio. So the music itself, which is currently playing through a tab, right? Like, I have to figure out how to separate that properly. And make it, like, its own thing. I guess I could make a browser source that was just Amazon Music itself. Anyway. Yeah, and I know a lot of other people are like, I can play whatever music I want now, and I'm like, I mean, true, but... So if a sub k converges, then the alternating series definitely converges. The sum of. Now we do have to put a, few caveats on this. So if a sub k decreases monotonically, and the limit, this should be pretty obvious at this point, but as k goes to infinity, the limit of a sub k needs to be equal to 0. Alright, that's true for literally every convergence theorem, right? If it doesn't converge to 0, or if the limit doesn't go to 0, then you're not going to get a convergence in the first place, so. And welcome to Arendelle as well. Alright, and then we go with and. This converges on. I can move two at a time, or whatever. Two separate moves. And that's not actually, hang on. Yeah, okay. We don't need the... Sorry. It's been a while. Right, a sub k doesn't need to converge by itself, because then that would be sufficient by itself to just be like, yeah, of course it converges. Of course the alternating series converges. Yeah, sometimes that happens. That's alright. It's been a few years since I've taught this, so like a lot of times it just pops out as something that I definitely have taught before, and I just don't remember the exact construct for how it works. But yeah, all we really need here is that a sub k is decreasing monotonically, and that it's going toward 0. The limit, the true limit, is 0. So with that, for instance, you can't tell if the harmonic series converges. In fact, it does not, and we can end up showing that. But so we know, for example, right, 1 over k, as k goes from 1 to infinity, does not converge. Right, for this, we could show it as, like, for instance, 1 over 1 plus 1 over 2 plus 1 over 3. plus 1 over 4. Right. So what we end up doing for this is we say that, let's see. All right, this is equal to 1 plus a half plus, now this term here is going to be greater than a half. These four terms, 1/5, 1/6, 1/7, 1/8, are greater than a half. And then we can keep doing this literally forever. It's going to exponentially increase the number of terms we need, right? We're going to keep doubling every time. When we get out to 1/16, we need all the numbers from 1/9 through 1/16 to be representative, but that's going to be greater than a half. And likewise from 1/17 to 1/32, all of those will sum up to a number that is greater than 1/2. And now if we add up all of these 1/2s, well, we're going on infinitely. So because we're going on infinitely, right, that's going to get us an infinite value. It does not converge. But as it turns out, right, if we go with k goes, here we go, -1 to the k plus 1 times 1 over k. Now I could totally cheat on this and be like, okay, well, you know, it just does because the theorem above says so. Does anyone have a better? I want to say it's something similar to that, but like no matter what sum we pick, it's always less than a certain value. And in the limit, that sum goes to 0. Or the sum no, it is, yeah, right. Because we're doing a 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus etc. How slow does it compare? How slow does it converge compared to 1 over k squared? Significantly, but I don't remember exactly what the. Oh. But your k squared is all positive, right? Okay. I think it's still significantly slower. So yeah, if we just do partial sums, right? Zach, look, it's chalk. Totally. Alright, 1, 2, 3, 4, 5, 6. Alright, 1, 3, nope. 1/2. Plus a third is 5, 6. Minus a quarter is 3/12 from 10 to 7/12 plus 1/5. It's gonna be 60. 12, and 35 is 47 sixtieths, minus 10 sixtieths, 37 sixtieths. There's got to be a way to do that, right? A. Add a slider for n. Yes, please. All right. That's not how that works. Never know. X. A. There we go. Knew there was a way to do it. One of these, and we do k squared, just for fun. Right, if we wanted to do this, like, only for discrete values, that might be helpful, but at the same time, like, meh. It's at least letting us see where all of this stuff is going. Yeah, it is significantly slower, but still, it's... Yeah. Okay, so if we go graph settings, make this go from -3 to 100. Yeah. Okay. And I guess if we wanted to... yeah. Now, what it converges to is also a very interesting question, right? So you have to... This is like an entirely different set of questions. Because when you start looking at, you know, whether it converges, that's not actually a terrible question. But when you start looking at, like, okay, now what does it actually converge to? Now it's like, Now you can always do what they did in the old days, which is you look at what the actual values are for all of these, and you go, that looks kind of familiar. I wonder if it's this amount. And then you go through and try to figure out, is that the particular value that I think it is? And in a lot of cases, it is. 1.67? So, sort of. Right? This is still like 1.635. It's getting real close to this. Yep. So that is one of the weird things. Is that you're looking for, or your actual value there is going to be pi squared on 6. And, like, a lot of people are like, okay, alright, that's enough. Where are you going with this? What? How is that even possible? Right, sum k goes from 1 to infinity of 1 over k squared is going to be equal to pi squared on 6. Yeah. So that's going to require some explanation. However, you know, you're like speaking truth here when we start looking at this and saying, okay, we're going to get pi squared out of 6 times the sum of the integer unit fractions, I guess, the squares of the unit fractions, right? And then being like, this is how we're going to derive pi, because I mean it comes out pretty nicely, and like you said, it resolves, converges like fairly quickly. So if we end up with a convergent value of pi squared by just saying, okay, we're going to do 6 times the sum of all of our unit fractions. What just happened? Music went away. Was it playing the last one? That doesn't make any sense. Okay. Well, we're going to this one then. I don't understand. It's bizarre. Fandom, good evening and welcome. Can we find an injective function f of x such that the sum over 1 over k squared from 1 to x is equal to f of x for whole numbers from 1 to infinity? Natural log of 2x? Or are we doing n on here? Ah, yep. Yeah, really, really close. I don't think it's quite there, but it might be. Okay. I could be convinced otherwise. Yeah, looks good to me. Far better mathematicians than I. Go from 0 to 6. Yeah. Anyway, Alright, can we find an adjunctive function such that the sum of 1 over k squared from 1 to x is equal to f of x? Yeah, Matt, no, Arundel was saying that if you plug in natural log of 2, that gets us the red line, which is then seemingly the limit for the alternating harmonic. Should be continuous, otherwise it's kind of trivial. Fair. So you're saying that we want a continuous function. Yeah, you know what I was trying to do originally was just put those individual sums as points rather than steps. And then I kind of forgot how to do it or something. I don't know. So you're saying we want f of x equal to... Okay, it goes from 1... Oh, right. So we want this as really f of n is going to be k 1 over k squared for define f of x such that we're going to have f of n equal to sum of 1 over k squared as k goes from 1 to n for all x equal n belonging to the positive integers. We've done that. We said that like last week in some way, shape, or form. Just draw straight lines, yeah. Yeah. Oh yeah, you could probably do that. Have to do something like convolution. Yeah, if you have like a hypothesis of, I think it should be this kind of function. Like if this looks like an exponential function that's been reversed, turned around, you could do something like that. So, hang on. There is a way to do this. How do you take a function and only pull values of x or whatever that are on integer values? Somebody's got to know how to do this on Desmos. I've probably done it before myself.
It's delicious.
Yeah, polynomials could be arbitrary, but this looks like, again, this looks like it's an exponential function that's been turned upside down. So in theory, we could say like, give me a... No, I need the points first, because that's me. So we could add a table. Let's go home. And then take this from 0 to just like 30. Not very many. And then from 0 to 6. Negative 0. It's all good. Oh no, it's purple's kind of the one we want. I'm gonna regret that. Is equal to, let's just make sure this works. Really? Alright, cool. Equations not allowed. Okay, so there we go. Okay, so it's there. Oh, come on. I'm not gonna just let it be also x1. Right, e to the x1. Right, we said that this was going to pi squared on 6. Oh, that kicks up above it. That's even worse. Wait, I can't kick above it. Oh no, it just gets there faster. Okay. So there has to be some value in here that we can plug in. Yeah, yeah. So if it was like 0.5, 0.9, nope, 0.1. Yeah, I mean, convolution isn't the correct answer, but but no one wants to do that. And that, and I haven't done it in 20 some odd years, so. Lazard, good evening and welcome. How you doing this evening? So, there's also, I mean, like, we do all sorts of stuff like this. Showing the true rate, more or less. And then if we... I want to reduce these to individual points rather than... Arg. It's gonna bother me. Yes, so I hang out in Zach's channel a lot, and then we also have been coming over to Matt's channel lately. When yeah, after we discovered Matt's existence. It's alright, Zach came over to my channel when he discovered my existence too. So it's good times. It was so sad though, because for the longest time both Zach and Penn Center were chatting in my chat, and I was like, this is great, you guys are educators, all this stuff, and they're like, yeah, we also have these Twitch channels. I'm like, of course you do. Like, I'm like, God, I'm not the only one. Yay. Yeah, so move forward. We're trying to figure out if there is a better approximation, or how to get a better approximation. There's always a better approximation. In order to figure out what continuous function would clip these sums at either the first or the last point. I'm not precious about which side it actually connects with, but whatever. So, like, we want this. Ideally, this would not be... this would not be a step function. That, like, our x would end up being... maybe int? We do... queen... nope. Floor? No, that's much worse. Actually, it does the same. I'm trying to remember. There's a way to do it in Desmos where you end up with all of the individual points and not these step functions. But Newton's method, cubic approximation, nice. Stuff like that happens, yeah. So I've been working in the community college space for excepting the last 2 years. The 15 years before that, I was working at a community college in Maryland, back in the U.S. And currently, I do stuff like this on Twitch, and then try to get my channel straight in terms of like putting it all on YouTube and making sure that there's like captions and stuff. But Yeah, it doesn't always work as well as I want it to. Not good at math, still doing well. Okay. Yeah, when I started getting colleagues who were born in 2000, I was like, oh no. Make some YouTube shorts. Definitely yes. Yeah, I mean Dr. Gold has got like just everything all over the place. Um, and it's something to look up to, certainly. And I definitely want to make more videos, but the problem is that I can't get, or I haven't in the past been able to get DaVinci Resolve to work, and like I don't want to pay some exorbitant fee to get Adobe because even though I know how to use Adobe, or at least I used to 2 years ago, even though I at least used to know how to do Adobe, like I'm not I'm not paying that amount, and B, that was 2 years ago. Uh, so I just feel like I need I need to make DaVinci Resolve work. It should have been 2 years ago that I did this, but I was in contact with a guy from who made a video on YouTube about how to make sure that it works with Linux, and there was some jiggery pokery that he had me doing, and it still did not work. I was just like, I'm giving up. So it's kind of sad. Caden Live. Have not heard of it. Does it work on -1/x? Oh, interesting. Is it just that simple? Is it just that simple? Oh no. Oh no. Very close, at least. Yeah, it is so close. Okay, so that's off by a constant. Hang on. This is here. That is like here. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3 and a half. There you go. That doesn't work either, but... Not too complicated. Functionality. Nice. Well, I will have to look that up then. Pop over here. Okay, I will set that aside and pop over to one of their things later and see how to install it via command line, because that's my preferred method. Make sure that, and also make sure that it auto updates. Did I make some kind of thesis on this? No. Anything that goes to 0 is going to look like it. Yep. So thesis would be like your final project. So like the big report that you would do for usually not a single class. Usually it's like your degree program, like the whole degree program. Or And my college, the University of New Hampshire, had bachelor's theses, master's theses, and doctorate theses available, like as possibilities. The bachelor's program also just allowed you to take as many classes as you needed and then be done with it. But I think if you did a thesis, it would like cut down on the total amount of work that you needed to do or something like that. Baccalaureate, yep. Obligatory, yeah. So there are other ones that do have uh, so offendum, it's close, but it's not quite there. This is the negative 1 over x plus pi squared on 6. So, like, this is here, right? It's not touching the ends. The continuous function probably does at 2.5. Yeah, that's weird. Well, you know what we have to do then? We just have to shift it like a half. Yeah, that one's also not quite right. It's again really close. It's messed up, man. What number's close to 0.55? Mavort, I don't, but we have a community community Discord, which is our kind of central repository for the edu Twitch / math community. So that link is for Penn Center's Discord. Let's give a shout out to Penn Center again because we're using his resources. So Penn Center is there and currently live. But then that is his Discord link. So again, it's called The Elements, which is named after Euclid's Elements, and all of us like Twitch streamer types who do math are usually welcome onto that server to be members of the faculty. How can we quantify the rate of convergence? That would also be interesting. So there is a way to do it. If you were to find f of x equals sum of k equals 1 to n 1 over k squared plus they often do like O of x. I usually prefer R of x just so that it could be like a little more obvious of what we're doing. R is going to be our remainder function. Right, we want to less for as it is from. find the continuous function from these discrete values. So if we find f of x is equal to this particular sum plus r of x, the remainder function, that's not actually what I meant, sorry. Right, because that's how it's defined up there. It doesn't work that way. You know, guess plus r of x, like that. Do I work on something as a teacher? So I did not have to. When I was at community college, the goal was that every semester you're just trying something new, and then that goes on your annual report at the end of the year. So you try to do something during the first half of the year, you try to do something else during the second half of the year, or refine what you did during the first half and like roll it over to do something usually also additionally new, but like in the same vein. So I was working on Building Thinking Classrooms by Peter Liljedahl. Now, I do not actually have the book right now because I lent it to one of my daughter's teachers. Well, I don't think he actually teaches her, but he teaches math anyway. It looks basically like this, but orange. This is modifying your thinking classrooms for different settings. This was his response, Peter Liljedahl, his response to COVID. So doing all the pandemic stuff. Everybody was scrambling, trying to figure out how to teach anything. And this is his, like, if you want to use my thing, which also came out in 2020 or 2021, it was like very unfortunate timing that his book came out right when people couldn't really use it. So they're like, these are brilliant ideas and concepts. How do we use them? And so he very quickly wrote a little primer on how to take his ideas over to like online and stuff like that. So I'm more interested in teaching methods and trying to teach like the individual things that like I was teaching in the community college, which is anything from basic math all the way up through differential equations, Calc 2, multivariate, all that good stuff. Ads are about to start. We are going to take a little stretch break. I will just snooze them for 5 minutes so we can finish this little bit of the conversation. But yeah, so I was more concerned with teaching methods and trying to do something different. One of the things that I'd come up with was like, oh, we're going to talk about doing the unit circle. But instead of like constantly just saying, you have to memorize all this stuff, my idea was we need to break it down so that it's much more obvious as to what we're doing and like what the students actually need to know from this. So, God, that's so bad. I think that's pretty close. Anyway. So my initial response was, okay, so we're going to start with our unit circle. We're going to say, okay, we want to fit an angle on our coordinate system. Right? Everybody else who's heard this 5 million times, I'm sorry, but, you know. Where's the best place to fit it? Well, if you put the vertex at 0, 0, then you've got this, like, well, I mean, we've seen radar maps and things like that. You've got this thing that's sweeping around from the middle. It's a perfect place to put it. And then, where do you put the 0? Well, putting it on the positive x-axis is just standard convention, but you could put it literally anywhere you want, and go in any direction you want. It's just that this is the standard mathematical convention. We do have the complete opposite version of this, which is headings, which start from 0 degrees north and then head clockwise. As opposed to here, where we start from 0 radians and head up that way, or 0 degrees and then head up and around that way, counterclockwise. So it's just all sorts of messed up, but you know what? It's fine. It works. Everybody will be able to realize what we're doing once you say, here's the way in which we do it. All right, so I took this and I said, I don't like the way that we are breaking things up. So what I said was, we're going to first just say, okay, how are you splitting up the unit circle? Go for like basics. Okay, we're splitting it down the middle sideways. Okay, so then here, this is 1, and this is 2, right? One of these things, 2 of these things. What are they? Well, we know that going all the way around the whole circle, if this were, if we want to look at the circumference, right? Circumference equals 2 pi r. So what if r equals 1? Okay, the circumference is 2 pi. So that means that, in this case, if we let r be equal to 1, we're going to have a circumference that goes all the way around the circle like that of 2 pi. What if we let that be the angle as well? This was mind-blowing to some of the students, but nonetheless. And then the standardization of everything was saying, okay, take r equals 1 here, and you say, if we take that r equals 1 and then wrap it around the outside of the circle instead, this is 1r. Okay, never mind r being specifically 1, but rather just let the whole circle, let the whole circumference be found in terms of radii, the number of radii you have. Then it doesn't matter how big or how small it is, it's always going to be the same. So this is going to be 1 radian. All right, this is nothing new. This is what everybody does. Right, this was done in high school. But again, if we go all the way around, it's 2 pi. So if we only go halfway, that's pi. Okay, that's your unit now. Pi. There's 1, 2. We're at 2 pi. Cool. All right, split it up again. All right, adds are going to actually go here. Sorry. This is pi over 2, because it's half of that pi. Now that's your unit. Where do you go? There's 1/2 pi, 2/2 pi, 3/2 pi, 4/2 pi. Right? Go for the quarters. Pretty close. There's 1/4 pi. 1, 2, 3, 4, 5, 6, 7, 8. Three minutes, be right back. So Lazat, if you do hate geometry, there's there's something that may be interesting and possibly make you absolutely rage quit, but nonetheless, if you've ever played Euclidia, this is basically proving proving Euclid's elements from like base principles, and you get to play around with it a little bit and try to understand it a bit better. I found it interesting. The save that's on my phone is up to like Epsilon, I think, Epsilon World. I'm trying to get 100% on everything. The save that I did here on stream is up to Gamma, and only about a sixth of the way through, so it's not. I don't take it personally, it's fine. Anyway, we're going to do a quick Tai Chi break. We learned a couple of new, or like a new move in the form, so that's going to be helpful. Apologies about the mess, my kids still have not picked up. We just have to withhold video games. I'm sure everything will be picked up very quickly. Alright, so Tai Chi Chuan is the slightly more combat version of Tai Chi, which is, you know, oftentimes people think of Tai Chi as like the thing the old ladies do in the park. Tai Chi Chuan is a bit more aggressive. And it starts from base principles. So the big one being that the Qi power of Tai Chi is not, in fact, a like mystical energy and all that, so much as it is a power that's being harnessed through biomechanics. So first off, in at least the modern world, we understand that we can kind of store energy in our energy and power in our body through simple biomechanical movements. One of them is tucking our body into what's called the inguinal crease, which is that location. It's literally a crease right on the inside of your inseam here, between your thigh and your abdomen. So if you notice here, if you're actually standing approximately shoulder width apart and feet forward, if you just kind of like twist a little bit, you can kind of feel that like the two parts of your skin kind of touch. And then if you bend a little bit more into it, it's not like it's compressing like a spring, but you can feel that there's something here, and if you twist out hard, then you end up getting much more power out of it than if you were just to like come from a standing position, bend your knees a little bit, and like try to do something, try to move side to side or what have you. Is that my wife's glasses? No, those are safety glasses. Okay. Anyway, so one of the things that we do for warm-up is, instead of doing like these windmills where you're going wildly like this, what we do is we kind of tuck our arm, but don't put any like massive energy into your arms. Let them kind of fall in front of you, and then what you do is you put a little bit of power into the inguinal crease and then push out, and it whips your arms around. And this in turn, because you're not putting any effort into it, allows you to warm up your shoulders a little bit better, and also your arms and things like that. And then we could do like Nordic skiing style here. Same deal. Don't try not to put any energy into it beyond like the first movement or so, and then you just use your hips to kind of push the hands forward and backward. And then we have another one that we do side to side. So let's switch which one's in front. This is basically using the same energy that you would for like getting yourself higher on a swing set, right? You kind of come down a little bit on the down swing, and then as it swings back up, you push back up again. And then 1 foot forward, 1 foot back. We do the same thing here. Rock back and forth. Try not to put any energy into your hands. Just let them fly as they may. We're trying not to do the slack thing like you might have if you went too high on a swing set, where like if you go into it, then make them fall. This is actually not very good for your shoulders or other joints. I can do it because I'm a trained professional. Alright, we always can switch back the other way. And we do a few more warm-ups when I'm in class. I usually do classes on Wednesday afternoons 1 to 2 and Saturdays. I'm not going to be there this weekend. Speaking of which, I'm not going to be streaming on Friday because I will be on a Air Force base, or rather Royal Air Force Base, with the Scouts. So I'm going to be elsewhere. Got my uniform and everything, man. Okay. So today we were learning about the Tiger Strike. Never close this properly. Gonna lose these expensive paints because it's just doesn't matter. Anyway. We were learning about a Tiger Strike. So basically, like, there is a particular position which we end up in the form where we have almost our entire weight on the back leg. Our front leg is basically touching the ground only at the toe, and we come from what's called the crane drying its wings, which is like this. My instructor says when he went to Malaysia, he actually did see cranes sitting out on the rice paddies like this, like drying their wings out. He said it was kind of interesting because it was like, oh, I just thought it was a metaphor, but no, you really got a crane doing this. So we come from here, and then let's see, I'm stalling. Bring the right arm. We're doing inner circles, so we come up. Nope, that's wrong. Inner circles the other way. So this is going to come from here and go out and around. This is going to come down and relax and come through, and then this is going to get in for a strike like this. So the hand comes in and basically is, you could also make it literally harder like this, which would make it quite an impact, or it could be more of a grab. It can be a literal just fist coming out like that. There's all sorts of stuff that can happen, but we'll get to it. So for Tai Chi, the form starts, feet together, kind of a relaxed stance like this. We step out, make the left foot now go forward rather than at a 45-degree angle. Then we turn the other foot to match. Cool. And then we breathe in, out, and then we roll onto the right foot here. Sorry. That's not what we're doing. We're turning on the right heel to go to the side. We have this like pretend energy ball that we have here. And then we shift all the way to the front and move the left foot forward. And here, as we shift this way, we're doing a ward off with the left hand and the right is kind of like holding back a little bit. And then from here, we tuck a little bit, come back with a ward off as we step with the right, and then turn the left foot, roll back, press, push, lean back, twist the body. We're in this weird like pigeon-toed stance. Keep twisting, and then we come around and do a single whip here, as well as our foot being now aligned 90 degrees the other way. And then all of this comes out, and then we twist everything and shift our weight all at the same time. Come down and go into lift hands, I think he called it. Almost no weight on the front leg again. And then we come back into like a slight guard position, and then move forward into a shoulder strike. And then here is where we start going into the crane here. And then as we move this, this is where we get the tiger strike here. That was supposed to be here. We're trying to clear something away from our body and over the knee. So it's hopefully going to end up over there somewhere. That's as far as we've gotten in the form. So I've been told that's about the first third, which is slightly alarming. We'll also do a karate form, which is a bit different. So from the art of Tang Sudo, we're going to do my black belt form. Which one? Basaidai. Good song for it. Nope, that way. Up blocks. Strike. Punch. Pierce. Whoop. Righto. And I get slightly less winded every time I do it. Change the category to sports? Nah. That's only a redeem. That doesn't count. I will, in fact, do a like karate stream at some point. I know that during the fundraiser that we were doing for Gotel, Game On to End Lupus. Yeah. So we were working with 8-Bit D and Coco Confession and a bunch of other people. Elbel, who are all either people who have or just allies of, friends of people who have lupus. So we did a bunch of we did a bunch of like possible redeems and stuff like that. There were a few people who like donated, and we got some stuff, but it was like, a $75 donation would end up getting you a make me do an entire like karate instruction stream. Nobody went for it, but I'm a small channel, so not really that surprising. Right. So we were looking at the unit circle, and when we started looking at breaking it up in different ways, we now have taking the whole 2 pi, splitting it in half, making it 2 halves of pi each, 1 pi, 2 pi. And then we said, well, what about halves, right? So now it's like this. We go from 0 to pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. Okay. And then we do quarters. So 1 quarter, 2 quarters, 3 quarters, 4 quarters, 5 quarters, 6 quarters, 7 quarters, 8 quarters. And it always counts up to 2 pi, like that's surprising or something, right? And then the other options were, okay, how else do you split up 360 degrees into like nice values? Well, it's not going to be pi over 8 anymore. This is 45 degrees, right? Pi over 4 is 45 degrees. You split that in half, it's 22 and a half. It's not particularly nice. It's fine, and there are other ways to work with those numbers, but unfortunately it also doesn't work for most trig applications. So then we said, if we split those into thirds, then we get those segments into thirds. Then we end up with 30-degree angle, or pi over 6 at the close values, horizontally close values. And then if we go to the upper values, those are going to be pi's on 3. And we can work with both of those. So we have nice numbers that we can work with, and that's too close. "15 years of eyeballing it helps, right?" This is going to be 1 pi on 3, 2 pi's on 3. 3 pi on 3 is pi, 4 pi on 3 is down here. 5 pi on 3 is over here. And 6 pi on 3 is 2 pi again. Pi on 6 is right here. 2 pi on 6 is pi over 3. 3 pi on 6 is pi over 2. Right? So 3 pi on 6 is the same as 1/2 pi. Right? 4 pi on 6 is 2 pi over 3. 5 pi on 6 is over here. That's a new one. 6 pi on 6 is pi. 7 pi on 6 is down. 8 pi on 6 is 4 pi over 3. 9 pi on 6 is 3 pi over 2. 10 pi on 6 is 5 pi over 3. 11 pi over 6 is the new one we have over here. And then 12 pi over 6 is 2 pi again. Now, why would I pick those values? Right, we have a very nice set of triangles that we can work with these two things. We have our 45, 45, 90, which we don't know what the values on the sides are, but we do know that the radius is just going to be 1 for most of this stuff, right? The unit circle has a radius of 1. Otherwise, we can scale up or scale down. And then we say here this is going to be Pythagorean theorem. X squared plus y squared equals 1, but x equals y in this particular case. So x squared plus x squared, 2x squared is 1. X squared is a half. X is, or absolute value of x is 1 over root 2, or root 2 over 2. Right, now what about the other one? Well, this makes an equilateral triangle. Right, so anyway. Right, this is going to be, well, this is a radius of 1, this is a radius of 1, and so this one must also be 1. It doesn't really tell us anything, except we also have a horizontal running across, which is the x-axis. And it splits it into two separate pieces, which then have to have the same angles. Right? If you're not sure that those two are actually equal angles, you could say, okay, well, what if it's just slightly off center? What if we built it off of, you know, this point instead? Well, then that would end up being an equilateral triangle like this way, and that's going to mess everything up, right? Not really. Right? Even if it's not 100% accurate, we can look at this and say, okay, well, we know that these are going to be right angles because we defined that drop to be an altitude. We know that the angle going up and the angle coming down are the same value as each other. So yes, actually we do know that those are equal. And now we have 3 angles and 1 side on each of them that we know are definitely the same value. So here we have, let's go with angle, side, angle. Right? Angle, side, angle. That's going to show us that these two triangles are identical to each other. They're congruent. So therefore, this side here and this side here must also be the same. Let's put 2 hashes on it. And if they're the same and their sum total is 1, that means that each of them must be half. And then what's the distance x going across until we meet up with the altitude? Well, here that's going to be 1 squared is equal to 1/2 squared plus x squared. Okay, so 1/2 squared is 1/4. So we get 3/4 is equal to x squared, and absolute value of x is equal to root 3 over 2. So that allows us to now find points for all of this stuff. So this point down here is going to be, we have a root 3 over 2 for the x value, but then also a negative, because we're going down, 1/2 for the y value. Also means that over on the far other side, we have a negative x value, so negative root 3 over 2 by negative y value, because we're going downward, negative 1/2. Okay, what about this one up here? Well, that's still in the negative x direction, so negative root 3 over 2, comma, but this is the positive y direction because we're going up, so 1/2. And then naturally pi over 6, both x and y are positive here, so this is root 3 over 2 by 1/2. So by doing some simple, like, Pythagorean theorem stuff, we now have 4 points, and we only had to figure out, really figure out what the x and y values were for the one in quadrant 1. In the rest of the quadrants, we just know that, okay, well, the x and y values were absolute valued to get those numbers. And then we just have to remember, like, oh, first quadrant is right and up, so x is positive, y is positive. In the third quadrant, x is negative and y is negative, because we're going left and down. Like, you don't have to memorize the entire unit circle. You just break it up into bite-sized chunks like this, and be like, okay, well, let's just remember how it works in quadrant 1. And once you've got quadrant 1, you could just think about the relationship that exists between quadrant 1 and quadrant 2, quadrant 3, quadrant 4. So doing this relational thinking is, in my mind, kind of what doing the math is all about. Right? And then the other thing that I'm going to toot my own horn here, I invented, now somebody else probably did it at some point, but I've yet to find any particular documentation. So, so if you wanted to talk about a particular target, so a location on the number line that you were trying to, like, hit with something. Let's say it's, I had thought of this originally as, oh yeah, everybody's favorite carnival game, throw a string at a string. There's essentially, like, those yard games, right, where you've got, like, the little, the bolo that you're trying to toss around the, like, PVC pipe that's at multiple heights. Right, this is basically what I was thinking of for this. So you're just taking, like, a string or something and tossing it over a yardstick. This is an easy classroom demo, right? Take your string, throw it over the yardstick, and land it on the yardstick as close to the target as you possibly can. Right, so you land up here. Let's say that the target is the number 6 for some reason. Doesn't matter. And you land, right, target. You land at the number 13. And then your opponent, who is going against you here, lands at the number -2. Right, different color. Opponent. Right, which one of you is closer, and how do you know? Well, it looks like the one that's at -2 is closer. So how do we measure this in actuality? Okay, find the distance between these two things. How do you find distance between two numbers? For this, we're trying to find the difference between these two numbers. So 13 minus 6 is going to get us 7. And -2 minus 6 is going to get us -8. So who wins, who's closer? Okay. So now we need to introduce the concept of, we don't care about what direction it's in. We care about how far something is. Right? But if we don't care about direction, we have notation for this. Okay, so obviously I did not invent the absolute value. That's just something that has existed for a very long time. Okay, but the way that I deal with absolute value is, in fact, different. So here we want the difference between 13 and 6 is going to be 7. The difference between -2, -6 absolute valued is 8. And so now we circle this one and say this one's smaller, so it's closer. Now, I'm not saying this so that you will go out and be like, let me find the particular distance between two objects on a number line. Like, that's not what you are probably going to be doing with this. You are probably going to be saying, hey computer, here's a list of 5,000 numbers. Find the distance of all of these particular things from a particular target. And, it could be different targets. It could be all sorts of stuff. So you're going to be going through and saying like, oh, well, I want I want the distance between a particular location, so that was x, right? The variable, which is the landing location, and our target. So x minus t, absolute valued, is going to be some sort of, again, this is a distance. Again, nothing that I have invented so far. However, when we look at this as something like, let's try to find the absolute value, the distance between x, some number, and 5, and say that the distance between those two objects is going to be 12. Right? I had a lot of students who were like, well, we take this and we make it equal to both 12 and -12 because, and they just kind of hand wave that away. Okay. If I ask them why, they can never answer me. So the thing that would really help you understand and be able to say, I really do understand what the concept is that we're looking at, is saying, okay, look, we've got a particular x value, we don't know where it is, but the distance between that particular x and our target value, 5. That distance needs to be 12. So where's that? Well, that's easy, right? It's on a number line. We just start at 5 and we add 12 to it. So we get 17. You don't even have to do any real mathematics here. You don't even have to write down the arithmetic. You already know this. You did this in probably 2nd grade, right? Start at a 5, go 12 away. That's a 17. However, we already specified that it didn't matter what distance or what direction it went. So that also means that we need to think about the location that is 12 in the other direction as well. So if we go down 12 from 5, well, we go 5, and then we have to go 7 more, so that's -7. And then we go to those locations because the distance was equal to 12. So now our x value is going to be either -7 or 17. That's it. Those are the only two values that are even possible. Okay, so this also works in a number of different ways. So if we were to do what's the distance Right, the distance between some unknown value, whatever our variable is here, and 8 is going to be less than 4. So our distance is, right, that gets you what it is that you're talking about, and the distance stuff is going to be over there on the other side. So we know it's going to be the distance is less than 4, and the distance is going to be an absolute value expression. Between some unknown value, again, x and 8. And again, if it's the distance, then it is the difference between them. And if that distance is less than 4, then we can draw this pretty easily. We have some unknown x, wherever that is. Our target value is 8. And the distance that it is away from 8, if it were 4, where would it be? Okay, that's 12, and that's 4. Again, don't even have to think about it. Okay, and then we say, well, the distance needs to be less than 4. So we can't be at a distance of 4. So these are empty circles at 4 and 12. And then the distance away from 8 is going to be less than. So we could be at 0 distance away from 8, or we could be up to 4, but not including 4 away. So we could be anywhere in between 4 and 12. And then here we just say that x is going to be anywhere along the interval from 4 to 12, like that, open. The distance between 7 and twice an unknown value is at least 9. Well, this is the same thing. It's an absolute value. The distance is at least, so it's greater than or equal to 9. The distance between 7 and twice an unknown value, that's 2x. Oh no, whatever shall we do? Don't worry about it. The distance is the same here. Our target value is still 7. It's the known value. Don't make your target value the unknown. That's just going to be silly. We want the distance between, so we are subtracting. What are we subtracting? We're subtracting 7 and 2x. 7 and 2x need to be the things that are on your diagram. We go to a distance of 9 away. On the low side, that's -2. On the high side, that's 16. At least 9 means greater than or equal to, so we can go 9, making these whole, right, solid. And then the distance needs to be more than that, or also more than that. So therefore, we go further away. Right, we're done, right? Not so much. Because we still have, this is not the values of x. This is the values of 2x. So what do? Well, we just take everything, and I mean literally everything, and halve it. What does that mean here? Well, our x is going to be somewhere between a -1 and a, outside of -1 on the low side and 8 on the upper side. solid circle still, and shade out still. There we go. X is going to go from negative infinity to -1 bracket, union with bracket 8 to positive infinity. Open. All right, and then students try to outsmart me by saying, okay, well, what if we had like the absolute value of, I don't know, negative x, negative 5x, let's just go crazy. Negative 5x plus 4 is going to be less than or equal to 3. I don't know, something like this. And honestly, this is no different. You could choose what to do here. What I'm going to choose to do is actually just reverse these, because this is just addition of 4 and a negative 5x. And now it's a subtraction problem, which is a distance problem, which is a difference problem. Difference between what? 4 and 5x. So again, we go 3 away. We go 3 away. That's 1, that's 7. And then the distance is less than or equal to, so solid circles shaded in. Alright, so then what about like negative 6x minus 7 is greater than 3? Right? There's a few different ways you can deal with this. One, you could just swap them. Negative 7 minus 6x. So now our target value is a negative number, and our variable is still a positive 6x. Oh, whoops. That was wrong. I forgot to divide by 5. Hey Afru, how you doing? Right, so here our variable term is still multiplied by 5, so we have to divide literally everything by 5. Yeah. And then again, same deal here. If the student thinks they're outsmarting me, I'm just like, okay, well, this is a very Tai Chi thing to do. Whoop. Just kind of redirect right over there. Right? We just move stuff around. We say, I want this to be a subtraction problem of subtracting 6x. So that the 6x term is now going to be, like, positive. We just have to make the minus 7 become a negative 7 plus, or a negative 7 minus the thing. Let's see, the other one, somebody else tried to get me with, like 3x plus 7 is greater than 4. So, again, in this case, it's not... This is not an issue. This is just, okay, I've already got a positive 3x. Good. Here, we just have to turn it into a subtraction problem. Right, so make it 3x minus a negative 7. And then that's just going to be, again, 3x here, negative 7 there, and 4 up there. And it's greater than, so it has to be shaded outward and open. Alright, for this one over here, this is greater than 3, so again, this is 3 in this direction, 3 in this direction. Here are your locations, open and shade it out. Yes, in actual problems I would be doing this, but, you know. No time. Let's move on. The only problem that this method really has is when you start doing stuff like the absolute value of 3x minus 7 is greater than 4x. Right, so it's less of a problem, it's just that it's slightly annoying. So for this, right, you'd be taking this and you'd say, okay, we've got 3x minus 7, and then the distance needs to be 4x. So here and here are going to be, again, open and shaded outward, but it doesn't quite work that way. So what we have to do now is say, okay, this is going to be 7 minus 4x. This one over here has to be 7 plus 4x. And we're saying that 3x is going to be equal... no, that's not true. 3x must be greater than 7 plus 4x. Or... let's go the other way. Move it over here. Or, because it's separate, right? It's or. 3x must be less than 7 minus 4x. Right, and so now we have some algebra to do, which is not a big deal, but yeah. You know. Negative 7 is greater than x. Or, not an issue, right? It's easy enough to figure out. Plus 4x plus 4x makes this 7x is less than 7, so therefore x is less than 1. So now we've got these two things. We want to draw it on here. X is going to be less than negative 7. Or x is less than 1. So, one supersedes the other because it's or. X is less than 1 is the only solution. Right, the x less than negative 7 is now superfluous, so we just don't need to write it. So, like, this method is fine when it comes to linear absolute value, even with linear equations on the, or linear expressions on the outside. It's okay. It's not great, but it's okay. If you try to do, I think the only one that got me was if you try to do absolute value is less than absolute value, then we end up having all sorts of problems. Because this doesn't play very well. So here, 3x minus 7, 4x plus 1. Right, this method is not going to play nice, because now you're talking about, well, we need the distance to now be absolute value, and which one is the distance versus the absolute value, it's going to be kind of messed up. So we typically don't do that. However, this did lead me to teach the algebraic version of this stuff ever so slightly differently. So if we just copy all this, okay. Now, most students, again, said, all I need to do is just eliminate the absolute value signs. And then do 7 minus 2x is greater than or equal to 9. And then 7 minus 2x and negative 9. and then they go, and then do I flip the sign this time, or was it the other time? Oh no, what do I do? And so I was like, okay, look, first of all, yes, you do flip the sign here because it's an inequality, but more importantly than that, why? And the answer always came down to, because I learned it that way, because my teacher told me, because, you know, nobody had a good answer. And I was like, yeah, my teacher told me too, and yet we're sitting here and it's like everybody's kind of wondering to themselves, oh no, what do I do? Which side? You know, and then why is it that if I flip the sign on the other side, so if this were negative parentheses 7 minus 2x, this would still be greater than or equal to positive 9. So I said, forget this, just go this way. Right? Make the side that came out of the absolute value negative. And then I thought to myself, now why is that? What's the definition of absolute value? Right? Absolute value of x is equal to this set of equations, right? It's x if x is greater than or equal to 0, and it's negative x if x is less than 0. So if we just change what's here and we make this 7 minus 2x, and that's telling us that it's just 7 minus 2x when 7 minus 2x is greater than or equal to 0, and it's negative parentheses 7 minus 2x when 7 minus 2x is less than 0. Right? Think about it in terms of basic principles. What are we actually doing? Okay, we could solve those out, but you know what? It doesn't really matter. We could just solve it from here. We know that 7 minus 2x is going to be greater than or equal to 9. Right? The distance needs to be bigger than a distance of 9. 9 is this far, so we need to be further. So that's telling me right there. That's telling me what this is going to look like. We're going to have 2 points and then arrows pointing outward. So this is going to be an OR statement because we want either of these to work. Either of these are going to give us the solution. So then here, this is just a matter of changing stuff around until we get a form we're happy with. So negative 2 is greater than or equal to 2x, or x is less than or equal to negative 1. Or, here, if we bring the negative in, this is going to be a negative 7 plus 2x is greater than or equal to 9. And then that means we just add 7 to both sides. And we get 2x is greater than or equal to 16, which is x is greater than or equal to 8. So x is going to go from negative infinity to negative 1, bracket, union, bracket, 8 to infinity. Open. Right, and then we should have gotten the same thing up here. Hey, would you look at that? Right, as long as you're getting the exact same answer in every eventuality, then you're good. Then if we really wanted to, we could find the breakpoint, which we already know from earlier, right? That was the middle here, our 7 halves. So if we look down here, right, when 7 minus 2x is less than 0, well, yeah, that's going to be 7 is less than 2x, or x is greater than 7 halves. And then the same for the other one, that this is going to be 7 is greater than or equal to 2x, which means that x is less than or equal to 7 halves. So it's the same breakpoint. We're just saying it a slightly different way. It's going to be in relation to that midpoint between the two branches. All right, ads are going to start. If anybody has any other questions about mathematics, let me know. I was just showcasing this stuff, especially because this pseudo-graphical method was something that I invented. I haven't seen anybody else do it. So if anybody wants any further explanation of cool stuff like that, let me know. And otherwise, I'll be back in 3.
I said I'm moving too far. Get to glass. Looking at a shooting star. Got more than a couple of people going mad. I swear they're rooting hard. Tell them I'd be big in the game like she went and got them breast implants. I said I'm moving too fast. Didn't even get to glance. I'm ready to eat up track like I'm seated in a restaurant. If you had swag like mine, you know it's best to flaunt. We aren't hating because you want. Shining like it's neon. Rock like kings of Leon. Shooting stars across the galaxy. I stand out, so don't be mad at me. Infiltrate with my strategy. When I turn up, them amateurs have to leave. Shooting stars across the galaxy. I stand out, so don't be mad at me. Infiltrate with my strategy. When I turn up, them amateurs have to leave. Yeah, shooting. Yeah, shooting. Yeah, shooting. Yeah, shooting shots. Didn't even get to cross. I said I'm moving too far. Get to glass.
Hey, welcome back. Appear to have dipped my glove underneath the faucet in the sink. Oh. Okay. So we discussed earlier the convergence tests that exist for, convergence theorem that exists for infinite series. So we discussed the alternating series just at the beginning here, and then we were trying to figure out like, well, okay, so the sum of all harmonic fractions, 1 over k, do not converge, and we can prove that pretty easily. There are an infinite number of 1/2s that we can make. In fact, right, a third plus a fourth is greater than a half. A fifth, a sixth, a seventh, and an eighth are greater than a half. A ninth, 10th, 11th, 12th, 13th, 14th, 15th, and 16th are greater than a half, etc. So since an infinite number of 1/2s being added together is going to be an infinite value, that series will diverge, and therefore this series diverges. But when we do the alternating series, where we take -1 raised to the k plus 1 and multiply it by 1 over k, this one does converge because we have the conditions from above. It is decreasing monotonically, right? It doesn't jump up at any point, and the limit is 0. That's it. That's all you need. As long as you have an alternating sign, you are increasing and then decreasing by a lesser amount, and increasing by a lesser amount, and decreasing by a lesser amount, and increasing by a lesser amount, and decreasing by a lesser amount, etc., etc. I think this actually is a good application of the squeeze theorem, because what we're going to say is that, like, assuming that there is some limit, our first number is, let's see, our first number was 1, so it's actually like way down here. And then it was a half, so we lose half that value. And then we added a third, we subtracted a fourth, added a fifth, subtracted a sixth, added a seventh, subtracted an eighth. So it ends up doing something like this. I think at some point you can argue that if you were to turn this into 2 like separate series, or separate sequences, they themselves are sequences, then you could show that no, that wasn't it. There's a good explanation of this. It might just be super easy and be like, well, since the next number is less than the previous number, the difference between them, right, is the value of the harmonic series. Since the new value is less than the old value, it'll never exit outside of a particular range. It's not possible. And then by the squeeze theorem, you say, like, it's bounded by this from above and it's bounded by this from below. And since it's bounded by each of those from above and below, and those things, crucially, those things have the same limit as this. Oh, the amount it increased was less than the other amount that we had, so it can't actually do this like upward stair step thing. It's not going to do that. Not possible. Right, this would have had been just larger, 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 larger. So that was 1 minus a half, up plus 1/3, down minus 1/4, up 1/5. Yeah, it's something like this. It's been a while since I've done that. Anyway. Yeah, actually, this is going to be subject to the squeeze theorem. Alright, so then the actual thing that we were supposed to get onto today, right? Alright, so a power series is one where we're looking at, again, the usual infinite series, but the internal portion of this is a power function. So we have some series of, or some sequence of coefficients, a sub k, but those are being multiplied by x, which is the standard x variable, right, raised to the kth power. So this is going to be, oh, and this can be 0. So we're going to go from k equals 0 to infinity. So this is going to be a sub 0 x to the 0 plus a sub 1 x to the 1 plus a sub 2 x squared plus etc. On out ad infinitum. So then here this is just going to be a0 plus a1x plus a2x squared plus dot 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 all the way out to whatever a sub nx to the n we want to talk about, but then that's just going to keep going. Right? It's infinite, so it just keeps going forever. Okay, so if we look at this as a power series, it could be also thought of as an infinite degree polynomial. But we don't really like that so much. We could also look at, like, when will this converge? And the answer is, well, it's actually not too bad when you look at it in terms of the ratio test, which is, again, a sub k plus 1 x to the k plus 1 over a sub k x to the k. Take the absolute value to make sure it doesn't do anything funny, and then we say, like, what's going to happen with this ratio? So this is just equal to the absolute value of a to the, or a sub k minus k plus 1 over a sub k times, here we have k x's at the bottom and k plus 1 x's on top. So we differ by a degree of 1. So then what is its relationship with the numbers 0 or 1 or infinity? And like, this is poor notation because infinity isn't well defined, but whatever, it's fine. Remember, the issue here is that if right, if right, this is L equals, that's important, right? If L equals 0, this converges. If L equals, what is it? Is it just 1 or is it anything? If right, if L is equal to infinity, then we get a divergence. And then if L is equal to some number n, finite and yeah, positive. I thought it was a different condition than that. No, no, no. It's always going to be positive because it's absolute value. But if all right, if n is positive and finite, then for what x values do we get the above? Outcomes, not conditions. Right, for what x values do we get those above outcomes? So when we look at this, is it going to be 0? Well, it's only going to be 0 if x is 0, or if the ratio between those two coefficients is 0. And again, we want the limit. Shameful, really. Limit as k goes to infinity. And what is its relationship with those particular numbers? I mean, 1 doesn't really matter so much, but n, some positive finite value. So for any particular power series, we might end up with yeah, I mean, realistically, we can even take x out because it doesn't involve itself with our limit, which is only in terms of k. So this is going to be the a sub k plus 1 over a sub k ratio, absolute valued. And yeah, we need absolute value of x as well. So, L equals 0 when either x is 0, which is trivial, because we want this to be true for all possible x values. Or when the limit as k goes to infinity of a sub k plus 1 over a sub k is itself 0. Right, L is going to be infinity. So L can only be infinity if, well, if we look at this and say, oh, when x is infinity, that's great, but again, that's only one particular value, and that's not even part of the limit. So we can just kind of ignore it for now and be like, all right, look, x is going to be a finite value. And even if it isn't infinite, like, or even if x is not finite, it's only at a particular point, i.e. when x goes to infinity. So it's not really interesting or important yet. So then we just say, what happens when the other thing goes to infinity? Well, that's going to be the key. Good evening, wisest boar. How are you this evening? My name is Obi-Wan Pez, and this is N Simplex Pachinko. We do mathy type stuff Mondays and Wednesdays. We hang out with other math Twitch people. The Edu Twitch community is fairly large and encompasses a whole lot of subjects. We're doing pretty well here, thanks. Anybody who's interested, these are most of our other friends who do work here on Twitch with mathematics in some way, shape, or form. Some of whom do more physics-oriented stuff like actual education and physics and depression. PhoboStream is more of a coder, but most of the rest of us do some form of math. We also have co-working streams. We have, amongst all of us, we have co-working streams, gaming streams, and all sorts of other stuff. So feel free and follow anyone you want, and slopes and all the stuff that comes with that. Specifically referring to like Algebra 1, or like, thank you for the follow, like calculus. Linear, yep. Yep, so I taught at a community college in Maryland in the USA for about 15 years. And I shouldn't say about 15 years, I got the pin to prove it. So if you want to drop any questions you have right in chat, or we do have a friend who has a Discord server. Nope. No. Don't do that. Oh, interesting. Okay. Tried to copy the thing that I had from... Anyway. That Discord server links to The Elements, which is the Discord home of all of those people. So if you look at that list, we have the where am I pointing? That list over there, or that list over there, wherever you have your chat. Oh yeah, no worries. Right, so then we want to know, basically, is the limit of the ratio of the coefficients going to go to 0, or is the limit of the ratio of the coefficients going to go to infinity? That's pretty much all we got. There is the possibility that it will be finite. So here, x x is going to encompass all possible values. Now that's true for all the other ones as well. So again, x equals 0 is a trivial possibility because it only occurs once. And then you've got the sum of like all these other things with all the other possible x's as well. So our x's raised to powers is going to be a function, right? It's going to exist as a big polynomial. So just saying, well, yeah, if x is 0, then we get the limit of 0. Like, okay. Okay, so x is going to encompass all possible values. And then we have to look at the limit k going to infinity of the absolute value a sub k plus 1 over a sub k equaling n, and then saying but we don't want it to be. So then we say, well, if x times, or the absolute value of x, times that limit, equals this particular n star or n or whatever we got, then we want to know what can we do? What particular values of x are going to end up getting us particular values of that limit? So we're going to have this absolute value of x is equal to, n star over our limit. Right, so now we want to know, when is this thing going to be between 0 and 1? No, that's not true. Sorry. When is this equal to 0? When is the limit going to be equal to 0? And then when is that limit also going to be equal to infinity? So for what x values? right? So for those particular values, absolute value of x times the limit as k goes to infinity of a sub k plus 1 over a sub k, where do you get 0 and where do you get infinity? By using the values of x. And so in some cases, you can get something that tips the scale a little bit and makes it happen one way or the other. Okay, so as an example, right, this will be easier if we use an example. If we get 2x plus x squared plus 8/9 x cubed plus x to the 4th plus etc. What series is it? What power series is it? And then also what power series is it? And then what are the values for the convergence? Right, so our a sub k have these particular values, right? 0, 2, 1, 8/9, 1, and then continues on. So for these, I don't actually see what the particular function is offhand. However, yeah, that'd be y. Okay. Alright, so these are 2 to the k over k squared. Where, right, k is going to be greater than or equal to 1. Or k is going to be strictly greater than 0 in this particular case. So here we don't have a 0 plus at the beginning. A sub 0 is just going to be assigned 0 for this particular sequence. So sum 2 to the k over k squared multiplied by x to the k as k goes from 1 to infinity. Right? So we want to look at this in terms of the ratio test again. So 2 to the k plus 1 over k plus 1 squared, all divided by 2 to the k over k squared. Take the limit as k goes to infinity and absolute value the whole thing. Okay, so then this is going to be limit as k goes to infinity of absolute value. 2 to the k plus 1 divided by 2 to the k is just 2, so that's going to be up top. Okay, and then down the... Well, okay, both. Multiply both top and bottom, we end up with k squared up top and k plus 1 squared on bottom. And we can also, in theory, also drop the k squared underneath, and so this ends up being uh, 1 plus 1 over k parentheses squared. Okay. This would have also been k to the, or x to the k plus 1 divided by x, so this gets us an x up top as well. As k goes to infinity, this bottom term goes to 0, and thus it's 1 plus 0, so 1 squared, just 1. So this is going to be x, absolute value of x, times the limit, so k goes to infinity, of absolute value of just 2. Oh, we already use, yeah. We already used the limit in getting the 2. Alright, so our L is just absolute value 2x. Okay, now if our x terms all end up being between 0 and 1, then all those numbers, when you throw them in, are going to get multiplied by themselves again and again and again. And eventually, all of these terms end up going to 0. So we can find whether it converges under certain conditions. So what values for x will cause this L to become 0? So here, this is L. We need this to be between 0 and 1 in order to get a convergence. So this is just going to be the absolute value of x is between 0. So since it's already positive or non-negative, we don't actually need the absolute values anymore. And 1/2 on that side. So our x can be anywhere between 0 and 1/2, not inclusive. And we will get convergence. So it's 2 to the k over k squared, x to the k. K goes from 1 to infinity. Right, it's going to converge conditionally, and if we look at the interval, 0 to 1/2, right, we could think of this as if it were a circle centered around, well, there's one point right in the middle. It's going to be 1/4. And then with a radius of, and this is just going to be 1/4. So our radius of convergence is going to be 1/4. Okay. Now the next question is, what about the endpoints? Wait, what? Oh.
Raiding party!
Hey Penn, how you doing? Hey everybody, it's Penn Center. Hope y'all are having a good evening. My name is Obi-Wan Pez. This is N Simplex Pachinko. If you haven't met me before, I'd be surprised. But we've got a few new people tonight, so awesome. Hope to see you all again. And if you're hanging around for a bit, awesome. And if you've got a raid and run or what have you, you know, can't say that I blame you.
I have a pen.
It has been a very long
I
day.
have an apple. Apple pen.
Pap. What's that? Wait. Apple. Yep. Hey, Collar. Good evening. P inverse AP. Okay. Okay. I just messed this up. So it's all good. It isn't actually going to... 0 is not actually going to stop us because for this particular setup, we have this absolute value of x being less than 1/2. The x value can be anything on the real number line. So negative infinity to positive infinity. Absolutely, Penn. Have a good break. Which then makes the bottom side not 0, but negative 1/2. Okay. So, all this stuff will converge conditionally. It must be within this circle, which now, again, this is also irrelevant. Ooh. Okay. We got a half here, and we got a negative half here with 0 in the center. So the radius overall is a half, not a quarter. Okay. So radius of convergence is a half. Goes from 0 to positive 1/2 and negative 1/2. Then we want to say, what about the endpoints? So at positive or negative 1/2 itself, what happens? So here we let x be equal to negative 1/2, and let x be equal to positive 1/2. What happens in each case? So we take the function, not function, but the series here. That is not what I wanted. Nope, nope, nope. Okay. Then here we take out the x and instead make it a negative 1/2 raised to the k. And then we also take the same thing and give it to the other one, only this time with a positive 1/2 instead of x to the k. So then what is that going to do? Okay, so what's that going to do? Well, this is going to be now a negative 1 to the k times 2 to the k divided by k squared times, here we get a 2 to the k that then pops underneath. Well, that's kind of fun, right? That divides out, and now we're left with the sum alternating of 1 over k squared. So this says that, first of all, 1 over k squared, it converges. So sum of negative 1 raised to the k over k squared also converges. Again, it's monotonically decreasing its value, and also we've got a positive and a negative amount that we're moving every time. So we're moving a smaller and smaller amount, and they're converging to a value that's between our upper bound and our lower bound of, the sums, the partial sums containing the last term positive and the partial sums containing the last terms negative. So it's always between these two things. They're coming closer and closer and closer together. It's going to converge. And we already know that because the this will absolutely converge. And so therefore the alternating series must also converge by p series if we really want to if we really want to make sure that we cover all bases, all that good stuff. So then we say, okay, what about when it's a positive 1/2 then raised to the k? Well, here we end up getting the same thing. This is going to end up being 2, nope, not 2k, 2 to the k over k squared times 1 over 2 to the k is 1 to the k, or just 1 over 2 to the k. And then again, we've got these. So this is now going to be the sum, as k goes from 1 to infinity, of just 1 over k squared. Nothing else. We already said it converges by p-series. So both of these converge, which means that the convergence will occur for all x values belonging to the real numbers, which also belong to now a bracket negative 1/2 up to positive 1/2 bracket. If anybody has any particular math questions that you'd like to ask, I'm pretty good with differential equations generally, and anything under that. So, Okay. Okay, so right, this is given. All right, this will converge for absolute value of x less than 1. This is well determined by our geometric series that we had talked about before when we were doing like the pre-calc session, and a couple of sessions in the like Calc 2 area of how do we do series. So the idea was that we had the sum of all a sub 1 times r to the k minus 1, where k went from 1 to infinity. Actually, from 1 to n. Right, using the geometric series formula, we had something that looked like a sub 1 times 1 minus r to the n over 1 minus r. We then took this as the limit of n went to infinity, and ended up getting a 1 over 1 minus r. And that was it. So for the above geometric series, k goes from 1 to infinity of just x to the k, start from 0. Which is 1 over 1 minus x. Okay, we can also then figure out what the use the series expansion to find a g of x is going to be equal to the log of, and this is again natural log of 1 minus x What we want is the power series expansion of that. B h of x is equal to x over 1 minus x squared. And C. J of x is equal to arctan of x. Okay, so to get the natural log of 1 minus x, this one's actually pretty easy because all we need to do is take the original power series that's up there and then take the integral. So this is going to be the integral of 1 over 1 minus x dx. Okay. The derivative of the bottom needs to be part of the chain rule, so we need a negative inside and out in order to satisfy that bit. So this is going to be the integral of the power series, k going from 0 to infinity, of x to the k, which dx. Which, for every single individual part, right, this is going to end up being that we get a x to the k plus 1 divided by k plus 1. No, sorry, that's already done. We need the sum as k goes from 0 to infinity. It's going to be equal to the negative natural log of 1 minus x. That feels a little weird, but I think that's actually right. So the natural log of 1 minus x is going to be the same as negative summation k goes from, I mean, realistically, we can shift all of our values from 0 to being 1 instead, and just have this be x over k. X to the k over k. Which is going to end up being, this is going to be a negative 1 with a 2. It's going to be a minus x squared on 2 minus x cubed. Oops, that first one is just x. Right. Negative x minus x squared on 2 minus x cubed on 3 minus dot 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 forever. Right, I think that's it. Yeah, shift your indices. Makes it easier. Alright, h of x is equal to x over 1 minus x squared. Right. So for this, we're letting... let u be equal to x squared. So du is 2x dx. And then the derivative of what was it? 1 over 1 minus x. It's going to be equal to It's not a derivative, is it? We weren't trying to get that. We were trying to start with power series expansion of just k to the x is equal to 1 over 1 minus x. Okay, so what we've got here then is 1 over, it's not this. This is equal to x times the series expansion of 1 minus x squared. With a term that has been changed. So here we need to compose. And here we need to multiply. So 1 over 1 minus x was 1 plus x squared plus x cubed, etc. X over 1 minus x is going to be x plus x squared plus x cubed plus x to the fourth, etc. And then x over, order of operations. Got to do the other one first. Order of operations matters. 1 over 1 minus x squared is going to be equal to 1 plus x squared plus x squared squared plus x cubed squared plus dot dot dot, which is 1 plus x squared plus x to the fourth plus x to the sixth, etc. So evens only. Then we got x over 1 minus x squared is going to be equal to x plus x cubed plus x to the fifth plus x to the seventh, etc. Right, so h of x is going to be that one. You have to do the composition and then you also have to multiply by x afterward. If you do the composition, or if you try to do the multiplication first and then do the composition, you have to replace both parts, and that's not what we want. We did not want x squared over 1 minus x. 1 minus x squared. Alright. this one's a little bit weirder. So because arctan, right, j prime of x is going to be 1 over 1 plus x, we have something in terms of 1 over 1 minus x. So this is going to have to be 1 over 1 plus parentheses negative x. Actually, sorry, minus negative x. There we go. Which is then going to be 1 plus negative x plus negative x parentheses squared plus negative x parentheses cubed plus etc. Last snooze. Right, etc. So then that's going to be 1 minus x plus x squared minus x cubed plus x to the fourth minus etc. So that one is going to be, we can also shorten this because we can make it sigma notation instead. K goes from 0 to infinity of. Coefficients are always just going to be a -1 alternating, starting with 0 being positive, so just k, times x to the k. Okay, that was it. And then we go the other way. We say, what about this other one back here? We didn't actually do the sigma notation for it. So k goes from 0 to infinity, and in fact, let's go from 1 to infinity instead. Odd powers. That's not an equals. Odd powers is x to the 2k minus 1. Going from x, or k equals 1. Or we could go from k equals 0 and have this be 2k plus 1. Either way. All right, we already did that one. Good times. That's not done, is it? Right. So we got the derivative, and now we need to actually take the integral and back it up. So j of x is going to be equal to the integral of all that dx, which is equal to, this is going to be x minus x squared on 2 plus x cubed on 3 minus x to the fourth on 4 plus etc. Which is the sum, as k goes from 1 to infinity, of alternating k plus 1 times x to the k over k. Right, this actually works, because we were able to multiply and compose to get that to happen. This, we started out with something that was a natural log but not quite right, and then we made it negative and it fixed everything. Okay. Did I read that wrong? I did. Man. This was supposed to be Yeah, it was supposed to be the other way around here. 1 minus x squared.
What do you expect me to say? You know that I will always find a way to fuck up everything that we ever made. Some people change and some people don't. Don't give it another shot. We've had enough, I think it's time to stop. I fucked up everything we ever made.
Okay, this was h, so h prime of x is equal to... No, not h prime. 1 over 1 minus x prime. It's going to be a negative 1 over 1 minus x parentheses squared, but then chain rule, the negative on the inside is going to affect the one on the outside. Okay, so that is going to be the derivative of the summation. The derivative of the summation was just x to the k, so now it's k times x to the k minus 1. K goes from... was it 1 or 0? Yeah, it was 0. But it's not going to be 0 anymore. It's going to be 1. Right, we could talk about that later. And then we need to make it x over 1 minus x parentheses squared. So that's going to be equivalent to sigma k goes from 1 to infinity of k times x to the k. Yep. Awesome. Okay, so that is actually the actual h of x. But we do have one where I read it wrong. Right, because if you ever need that other stuff, that's the way to do that. Okay, we gotta raid quick over to somebody. Probably Dr. Gold if he's on. What do we got? Oh. I don't see Dr. Gold on here, so let's go see Dr. Danny Anduza, who's over at Paleontologizing, talking about dinosaur news tonight. So, if anybody's interested in paleontology and dinosaurs, this is your guy. Definitely follow Dr. Danny. I will be back on Monday for more mathy stuff. Taking a few days off, going to another Royal Air Force base and seeing some scouts. So, we'll see you all later. My name's Obi-Wan Pez. This is Ensign Flex Pachinko. Have a good night.